did you know that the light you see falling through the night sky isn't actually a star dying, but rather a piece of cosmic dust, perhaps no larger than a grain of sand, igniting itself into brilliance as it collides with the invisible boundary of Earth's atmosphere? This happens thousands of times each night across the planet, in a silent and ancient ritual that has been unfolding since before humans learned to read the stars. There is something profoundly quieting about standing beneath a meteor shower, not the rushing sensation you might expect, but rather the opposite. Time seems to slow. The ordinary world, the concerns of the day, the weight of things unfinished, begins to dissolve into the soft darkness around you. Your eyes adjust to the night, and slowly, gradually, the deeper sky reveals itself. Not all at once, but in gentle waves of perception, as if the universe itself is turning toward you with infinite patience. In these moments, beneath the falling light, something shifts in the human mind. You find yourself waiting, watching, breath slowing to match the vast, unhurried rhythm of the cosmos. A meteor will appear, arc across the sky in a luminous whisper, and vanish. Minutes pass. Another one glimmers into existence, then silence again, long silence. And in that silence, without any instruction to do so, your body begins to let go, your shoulders drop, your breathing deepens. The space between thoughts grows wider. This is the peculiar gift of meteors. They teach us, through their own fleeting lives and their ancient journeys, that there is a rhythm beneath all things, that some of the most profound experiences arrive in silence and solitude, and that waiting, truly waiting with an open heart beneath the night, is its own form of peace. If you find yourself drawn to these slow, science-rich journeys through the quiet wonders of space, where facts about meteors and celestial phenomena become gateways to deeper stillness, I invite you to subscribe. We explore the night sky not for excitement or spectacle, but for the profound calm that comes from understanding the ancient, patient movements of the universe. So let us drift now into the story of these falling lights. Let us understand what they truly are, where they come from, and why their journey through our sky has captivated human consciousness for tens of thousands of years. Because once you know the real science of meteors, once you understand the gentle, almost tender physics that brings them into our night, the experience of watching them shifts entirely. They become less distant miracles and more intimate companions in the dark. On this particular quiet night, imagine yourself in an open field. There are no city lights here. The darkness is complete and enveloping. Above you, the Milky Way stretches its pale river across the sky, a sight our ancestors knew intimately, but which has become rare for those of us who live beneath artificial light. Your eyes have been adjusting for 20 minutes now. The stars emerge slowly, first the brightest, then fainter ones, until the sky transforms into something alive and textured, a visible cosmos instead of a flat black void. You are waiting for a meteor. You have read the forecast. Tonight is the peak of one of the major showers, a night when Earth is passing through a stream of ancient comet debris, and the display will be particularly rich. But waiting is the essential part of this experience. Waiting in the dark, waiting without expectation, just watching, letting your attention soften and expand across the whole dome of sky above. And then, perhaps without warning, a thin line of light sketches itself across the heavens. It does not streak across dramatically. Instead, it simply appears, a graceful arc of luminescence that traces its path for perhaps a second, maybe two, before fading back into darkness. But in those brief moments, something happens. Your breath catches, not from fear, but from a kind of wonder that feels almost pre-conscious, as if your body recognizes something ancient in the gesture. The falling star, the gift from above, where did it come from? The question arises gently in your mind. And the answer, when you learn it, is even more extraordinary than the myth. This light was created by a particle of matter that has been drifting through space for thousands, perhaps millions of years. A fragment of a comet that passed near Earth long ago, its trajectory curved by gravity into an eternal orbit. And tonight Earth, in its own ancient circuit around the Sun, passed through the path of that comet's debris. This tiny particle, perhaps the size of a pebble or a grain of rice, hit the upper atmosphere at a speed of 40 miles per second. The collision with the air molecules surrounding it created friction. That friction created heat. That heat caused the air itself, not the particle, to glow. And you, standing in the darkness below, witnessed the result, a brief, luminous death that illuminates the night. This happens constantly. Even now, while you read these words, thousands of meteors are falling. Most burn up completely in the thin upper atmosphere, never reaching Earth's surface, their brief lives ending in silent glory. And those that do survive the fiery descent, the rare ones that hit the ground, are called meteorites. They have their own stories to tell. But the meteor shower you are watching tonight is different. These are purely celestial events, pure light, pure transformation. As you stand there, another meteor falls, this one moving more slowly than the last, tracing a longer arc. Your mind quiets further. Time loses its rigid structure. There is only the waiting, the watching, the occasional flash of light, and the vast, patient presence of the night around you. This rhythm, the long silence between meteors, the brief illumination when they come, begins to align with something inside you. Your breathing follows the pace of the sky. Your thoughts, usually so rapid and insistent, begin to space themselves out like the falling stars. This is what the ancient peoples must have felt, you think, before clocks, before schedules, before the artificial structures that keep our modern minds always rushing forward. Humans lay in the grass on nights like this and watched the sky fall slowly open. They had no explanations, but they had something equally valuable: direct, unmediated experience, connection. The knowledge, without words or science, that they were part of something far larger than themselves. And now, knowing what we know now, understanding that these lights are ancient cosmic matter, dust from the birth of the solar system itself, completing journeys that began before Earth was fully formed, does not diminish that experience. If anything, it deepens it, because now you know that you are not just watching light fall from the sky, you are witnessing time made visible. You are seeing the slow unfoldment of the universe's own story, written in trails of luminescence across the dark. Your eyes remain fixed on the zenith, that point directly overhead where the most meteors tend to appear. The night air is cool, there is no wind, or very little, just a gentle stirring of breeze that reminds you of your own breathing, that you are a living thing suspended in space, part of this same sky, made of the same ancient stardust as the particles now burning their brief journeys above you. Time continues to dissolve. Thought becomes increasingly sparse. You are simply present, simply watching, simply being held, without knowing it, in the profound stillness that only the night sky can offer. Another meteor, and another, minutes later, each one a small punctuation mark in the vast, patient silence. And with each one, your mind releases a little more of its grip on the day. Worry fades, obligation fades. The future, which loomed so large during daylight hours, retreats into irrelevance. There is only now, only the darkness, only the gentle, falling light. If you've ever found yourself drawn to the quiet mysteries of the night sky, wondering about the stories written in light above us, then what unfolds in these slow journeys through space and time might become something you return to again and again. There is a particular kind of knowledge that settles into the mind not through urgency or spectacle, but through patience, through the gentle accumulation of wonder that comes when you learn the true nature of things falling from the darkness. Meteors, you see, are gateways to understanding not just our own atmosphere, but the very fabric of how worlds are born and how they age across the vast rhythms of the solar system. And if the thought of exploring these quiet marvels appeals to you, the slow science of ancient light, the patient witnessing of celestial events that repeat with the seasons, the kind of knowledge that deepens each time you look up at the night, then I'd invite you to subscribe to this channel. Here, we build these narratives slowly, piece by piece, fact by fact, letting each discovery settle into your mind like starlight filtering through the atmosphere. Our commitment is to bring you these deep, science-rich journeys through the quiet wonders of space and sky, stories that honor both the rigorous truth of what we know and the genuine awe of contemplating it all. The streaks of light you see in a dark sky are invitations to understand something profound about where we are in the cosmos. They are echoes of ancient collisions, fragments of ice and rock that have been drifting through space for millennia, waiting for the moment when Earth's orbit carries us through their path. And when we sit with these facts, when we let them unfold at their own pace, they begin to reveal a much larger story about time itself, about how the solar system was born, how our planet has been shaped by cosmic events both violent and graceful, and how we, as observers on this small world, are connected to everything that falls from above. With each meteor shower that returns to the sky, there is an opportunity to witness something that humans have watched for as long as we have existed. And that continuity, that connection to something ancient and ongoing, is part of what makes these phenomena so deeply settling to contemplate. What we explore together here moves beyond the simple fact of meteors appearing in the night. It ventures into the physics that describes how a piece of space rock becomes incandescent in our atmosphere, the chemistry that reveals what such materials tell us about the birth of our solar system, the history of how humanity slowly transformed its understanding from fear and superstition into curiosity and careful observation. We consider the mythology that shaped how ancient peoples made sense of these falling lights, and we trace the patient work of scientists who, over centuries, convinced the world that stones truly do fall from the sky. We wander through the mechanics of how Earth's orbit intersects with debris trails left by long-dead comets, creating the rhythmic meteor showers that mark our calendar year after year. And we sit with the poetic reality that these visible streaks represent the brief, brilliant ends of objects that have traveled across the solar system, sometimes for longer than human civilizations have existed. If you choose to subscribe, you'll be joining a community of listeners who prefer their knowledge served slowly, who understand that the deepest understanding comes not from speed, but from presence. You'll receive more of these narratives, each one designed to be heard in the quietness of evening or night, each one built to let facts and wonder accumulate together in your mind. We'll continue to explore the night sky not as a collection of trivia, but as a living archive of cosmic events, a story written in light and dust and the mathematics of orbital mechanics. From the physics of atmospheric entry to the composition of meteoroids, from the cultural traditions of meteor watching around the world to the latest technologies that allow citizen scientists to catalogue fireballs in real time, these journeys will unfold at a pace that invites reflection rather than rushing toward conclusion. The work of understanding meteors is, in many ways, the work of understanding our place in a universe that is vastly older than we are and infinitely larger. It is the work of holding in mind the scale of time, millions of years of cosmic dust drifting between worlds, converging in moments of luminous beauty that last only seconds. And when you subscribe to follow these narratives forward, you're choosing to make that work part of your own life, to set aside time each week or each month to sit with knowledge that calms rather than agitates, that deepens rather than overwhelms. That is the invitation we extend here. not to rush through information, but to drift through it, as slowly as meteors drift through the vacuum between stars, letting each discovery settle into the quiet spaces of your mind. There exists a peculiar puzzle in our language for the night sky, one that astronomers sorted out only gradually, and one that still confuses most of us when we look upward. We use the word falling star so readily, so naturally, and yet what falls from the sky is not quite a star at all. And the words we've chosen to describe these visitors, meteoroid, meteor, meteorite, each one names a different moment in the same journey, a transformation that happens in mere seconds as stone from space becomes light, and then, perhaps, becomes stone again on Earth. To understand this is to understand that there is no such thing as a single falling star. There is only one object, changing its identity as it moves through stages of its descent, much like a caterpillar transforming, though far more briefly and with immeasurably higher stakes. Begin with the meteoroid, out in the darkness between worlds, in that vast and mostly empty region we call space. There exist fragments, tiny pieces, some no larger than grains of sand, others the size of boulders, drifting in orbits around the sun. They are stone and metal, and, sometimes, ice. They are ancient. Many of them have circled the sun for billions of years, having been knocked loose from asteroids or shed from the tails of comets that passed through the inner solar system long ago. A meteoroid is simply this fragment, while it remains out there in space. It is just a rock, silent and dark, moving through the void at tremendous speeds, sometimes tens of thousands of miles per hour, yet moving so slowly through the vast distances that separate stars that it takes years, decades, centuries for any visible change in its position. When we say meteoroid, we are describing it in its natural state, untouched by any atmosphere, unobserved by any eyes, perhaps never to be seen by anything at all. But something changes when that meteoroid's path happens to cross with Earth's path. This is the nature of orbits. They are not fixed lanes but rather probabilities, and sometimes the probabilities align. The meteoroid begins to fall toward our planet, drawn by gravity, accelerating as it comes closer and closer to the sphere of air that surrounds us. And in that moment, the moment when the meteoroid enters our atmosphere, when it becomes subject to the friction of countless molecules of nitrogen and oxygen that fill the sky above us, it becomes something new. It becomes a meteor. This is the flash of light you see on a clear night, the streak across the darkness, the thing our ancestors called a falling star. The meteor is not the rock itself. It is the rock's interaction with our world. It is the energy released as the stone's tremendous velocity collides with air molecules. It is the heating and ionization of those molecules, the creation of plasma, that brilliant visible light. The meteor is transformation. The meteor is an event, not a thing. And this is the part that makes the journey truly remarkable, if the stone is large enough, or enters at a shallow enough angle, or is composed of dense enough material, then some of it will survive the journey through the atmosphere. The outer surface may burn away, ablated by heat. The interior may crack and cool, but a portion, sometimes most of it, sometimes only a small fragment, will continue downward through the thinning air until at last it falls to Earth's surface, slowing as it comes into denser air near the ground, eventually hitting soil or rock, or far more rarely, the ground near a living creature. In that moment, when it comes to rest on the solid Earth, it transforms one final time. It becomes a meteorite. A meteorite is what remains. It is the physical object you could hold in your hand, turn over, examine for its markings and composition. It is the rock returned home, carrying within it a record of the solar system's youth. Consider the elegant simplicity of this three-part naming scheme when you think about it. Meteoroid while traveling the void. Meteor as it burns and glows in our sky. Meteorite, once it has fallen silent and still on the ground. The same object, the same journey. Three names that mark three distinct phases. Most meteoroids never make the passage. They drift through the cosmos forever, unknown, unseen, completing their orbits in darkness. Of those that do enter Earth's atmosphere, far more become meteors than become meteorites. The vast majority burn up completely. They give their light to the night sky and then dissolve into dust so fine that it mixes with the atmosphere, becoming part of the very air we breathe. Perhaps that is why meteors hold such wonder in us. They are temporary, they are borrowed time. A meteorite, by contrast, is permanence. It is a message delivered across space and time, a fragment of the cosmos that chose to stay. And here is a thought worth sitting with as your mind drifts. The meteorite in a museum, the one a scientist examines under a microscope, the one that traveled for billions of years through the solar system only to fall in a particular field on a particular night. That meteorite and the meteor you might see streaking across the sky above you are not two different things, but two moments of the same story. The sky's brightness and the stone on the ground are separated not by distance but by time, by the thickness of atmosphere, by chance and physics, and the slow mathematics of orbital mechanics. When you look upward at a dark sky and see that sudden brightness, you are witnessing not a star falling, but rather the final chapter of an unimaginably long journey, a moment of transformation that will last perhaps only a second, a moment when ancient stone becomes light, becomes memory. Imagine standing at the mouth of a cave, perhaps 40,000 years ago, when the night sky held mysteries that no human had yet named. A streak of light suddenly crosses the darkness, brief, silent, inexplicable, and vanishes. What would you have felt in that moment? There are no written records from those earliest encounters with meteors, no cave paintings we can definitively say depict falling stars, and yet we know with certainty that our ancestors saw them. They watched the same phenomenon we watch now, the same stones falling through the atmosphere, burning and bright against the black. For millennia before anyone understood what meteors were, they belonged entirely to the realm of wonder and dread. Early humans, living beneath unpredictable skies, developed a relationship with these events that was deeply spiritual. A meteor shower must have seemed, to the unschooled eye, like a rupture in the fabric of night itself. The stars, which were fixed and eternal and dependable, were suddenly moving, falling. Perhaps early peoples wondered if the sky itself was breaking apart, or if the heavens were weeping light. We can only speculate at the stories they told around fires after witnessing such an event, but we know that no phenomenon visible to the naked eye goes uninterpreted for long when humans are watching. As civilizations began to form, in ancient Mesopotamia, in Egypt, in the river valleys of China, meteors became incorporated into systems of meaning. They were not merely curious natural events, they were messages, omens. The Babylonians, those careful observers of the night, recorded meteor falls in their astronomical chronicles. They did not yet know what meteors were, but they knew that they mattered, that they occurred in patterns sometimes, in clusters at certain times of the year. They tracked them, they wrote them down. In a sense, the first astronomers were not trying to understand meteors as physical objects falling through space. That understanding would come much later, but rather as signs pointing toward meaning in the human world. The ancient Egyptians watched meteors stream across their night sky and interpreted them as messages from the gods, as divine communication written in light. When a particularly bright meteor fell, what we now call a fireball, a meteoroid large enough to produce an exceptionally luminous trail, it was an event of profound significance. It could portend the rise or fall of a pharaoh. It could signal a year of plenty or a time of hardship. And in reading these signs, the ancient peoples were not being foolish, really. They were doing what humans have always done when faced with phenomena they cannot yet explain. They were creating frameworks of meaning. They were telling stories that made the inexplicable feel, for a moment, as though it had been accounted for. In China, the tradition of meteor observation runs back at least 3,000 years, preserved in texts and records of remarkable specificity. The Chinese developed a sophisticated system of what we might call astronomical omen reading, and meteors held particular weight. They appeared in imperial chronicles. A meteor falling in a certain direction, burning a certain color, lasting a certain length of time. Each variation carried different implications for the empire, for the cosmic order, for the stability of the realm. The Chinese understood, without yet knowing the physics involved, that meteors were rare enough to be meaningful, but common enough to form a pattern. They understood rhythm. They understood that something was happening in a cycle, even if they could not yet name what it was. Indigenous peoples across the world developed their own relationships with meteors, wove them into mythologies specific to their lands and cosmologies. Among many Native American traditions, falling stars were understood as spirits, or as messages from the realm beyond the visible. Some tribes spoke of stars falling into the earth as seeds of meaning, as communications from ancestors or from the spiritual forces that animated the world. These were not errors of understanding exactly. They were different frames for encountering the same phenomenon, frameworks that made sense within the knowledge and values of their own worlds. What connects all these ancient perspectives, whether Babylonian, Egyptian, Chinese, or indigenous, is that common thread of attention. Humans have always been watchers of the sky. We have always known, on some level, that what happens above us matters, and in those long millennia before telescopes and spectroscopy and orbital mechanics, the watching itself was enough. The act of paying attention to meteors, of recording them, of creating meaning around them, created a kind of knowledge. It created an archive, however mythological its expression, of the fact that these things happened, that they happened repeatedly, that they were part of the rhythm of existence. Consider for a moment what it must have felt like to live without the scientific explanations we now possess. To see a bright object streak across the sky and have no framework for understanding it, except the frameworks you inherited, the stories your people told, the spiritual beliefs they held. There would have been wonder in that. There would have been a kind of openness to mystery that we perhaps have lost. And yet there would also have been an effort to create order out of chaos, to make the unpredictable feel, in some small way, predictable through interpretation and ritual. As centuries turned into millennia, as different civilizations rose and fell, the observation of meteors continued. The practice of watching, of recording, of creating meaning became embedded in human culture. In medieval Europe, meteors were read through a Christian lens, divine signs, perhaps warnings, perhaps gifts. In the Islamic world, scholars developed increasingly sophisticated astronomical knowledge, while still honoring the traditions of omen reading that had come before. Everywhere that humans looked up, meteors fell, and everywhere that humans watched, they tried to understand. There is something profoundly soothing in this long human history of attention. It suggests that even before we understood what we were seeing, we were doing the right thing by looking, that the act of witnessing itself was enough. And even now, even with all our modern knowledge of meteoroids and atmospheric friction and orbital debris, we still feel that same pull when we see a meteor. We still look up. We still wish. We are still, in a sense, those ancient peoples standing at cave mouths or beneath vast open skies, marveling at the falling light, creating meaning from what the darkness sends down to us. The ancient peoples who watched these lights streak across their skies developed stories to explain what they were witnessing, and in the quiet of their own myths lay some of the deepest human attempts to understand a cosmos that felt both intimate and infinite. The Greeks, those philosophers and storytellers whose voices still echo through our language and thought, saw meteors as signs of divine attention. They called them shooting stars, or sometimes the tears of heaven, and many among them believed these descending lights were messages from the gods themselves, moments when the immortal realm reached down to touch the mortal world below. Aristotle and others in the classical tradition developed theories that meteors were actually phenomena born within Earth's own atmosphere, exhalations and vapors that caught fire as they rose, burning themselves into visible traces against the dark. It was a reasonable guess, grounded in observation, yet it missed the cosmic truth that lay hidden until centuries later. Still, there was something almost tender in their certainty that the sky was trying to communicate, that those brief flashes were not random or mechanical, but purposeful gestures. The Chinese civilizations, whose astronomical records stretch back further than almost any other culture still in continuity, kept meticulous accounts of what they called falling stars, and they wove them into the intricate symbolism of their cosmology. In the classical Chinese worldview, meteors were interpreted as harbingers of change, often connected to the fate of emperors or the stability of dynasties. A brilliant meteor might indicate the imminent rise or fall of a ruler, a disruption in the celestial order that mirrored disruptions in the earthly realm below. This reflected a deep philosophical assumption that was fundamental to Chinese thought: the idea that heaven and earth were not separate domains but profoundly intertwined, that the movements of the stars and the tumbling of lights through the night sky were expressions of universal principles that governed both the cosmos and human affairs. The imperial court maintained official astronomers whose sole duty was to observe the heavens and interpret what those observations meant for the empire, and meteors were never considered mere curiosities but serious matters of state, worthy of detailed notation in the official chronicles. Imagine standing in an ancient Chinese observatory, in the measured stillness of night, with the weight of empire depending on what you reported about a single thread of light. Indigenous peoples across the Americas, from the Arctic reaches down through the Great Plains and into the tropical forests, developed their own rich interpretive traditions around meteors, often seeing them as ancestors visiting from the spirit world or messages from beings who dwelt in the realms beyond the visible. Among many tribes and nations, meteors were understood as communications from the other side, brief visits from those who had passed beyond, or from spiritual powers that occasionally chose to manifest in the night sky. Some traditions held that a falling star represented a spirit falling to earth, beginning a new journey or completing an old one. Others saw meteors as signs that the boundaries between worlds were particularly thin at those moments, that the barrier between the living and the ancestors, between the physical and the spiritual, had grown permeable enough for light to pass through. The seasonal appearance of meteor showers would have been observed with reverence, woven into ceremonies and stories that connected the people to the turning of the seasons and the great cycles of life and renewal. There was a wisdom in these interpretations, an understanding that the falling of light from the sky was significant, that it meant something, that the universe was not indifferent to those who looked upward. Across cultures separated by vast distances and time, we find a consistent theme. The sky was alive with intention, and meteors were its language. Whether interpreted as messages from gods, as omens written in light, as ancestors visiting, or as expressions of cosmic order and earthly consequence, these early explanations all shared something profound. They refused to see the night sky as merely physical or mechanical. They insisted that what happened above mattered to those below, that a falling star was not simply dust burning away, but a meaningful event, a word spoken by the universe in a language humans could learn to read. This impulse to find meaning, to connect the small human life to the vast movements of the cosmos, is perhaps one of the oldest and most quietly beautiful aspects of human consciousness. The mythologies differ in their details: Greek, Chinese, Indigenous American, African, Polynesian, each carrying the unique voice and understanding of its people, but they are united in their refusal of mere accident. A meteor, in all these traditions, was never just a meteor. It was a sign, a word, a gesture that implied a listening universe. There is a kind of poetry in recognizing that our ancestors stood under these same showers of falling stars and saw in them the reach of something greater than themselves. They did not know, in the way we know now, that these lights were fragments of ancient comets, debris trails following orbits that have existed for millions of years. They did not understand the physics of atmospheric friction or the chemical reactions that produce that particular quality of luminescence, but they understood something else, something that science would later confirm in its own austere language, that meteors are indeed visitors from another realm, that they carry information about the history of our solar system, that they connect us to a cosmos far older and vaster than our individual lives. The mythologies were wrong in their specifics, in their literal explanations, yet they were correct in their fundamental intuition, that meteors matter, that they carry significance, that to watch them fall is to be touched by something beyond the ordinary. The myths held the truth about meaning, while remaining innocent of the facts, and facts and meaning would, in time, begin to converge as understanding deepened. And yet, for all those centuries of wonder and interpretation, the world still held a curious certainty. Those stones that fell from the sky were not stones at all. They were products of the earth itself, perhaps rocks knocked loose by lightning, perhaps volcanic ejecta lifted impossibly high and falling back to the soil that birthed them. The idea that objects could arrive from the heavens, that the vast distance between the earth and stars could be crossed by matter, seemed to contradict everything the natural philosophers of the medieval and Renaissance periods understood about how the universe was ordered. The celestial realm, after all, was supposed to be perfect and unchanging. The terrestrial realm below was corrupt and subject to decay. The two were fundamentally separate, divided by an unbridgeable gulf. So when a stone fell from the sky and struck a field, or landed near a village, the simplest explanation was the most comfortable one. It must have come from somewhere already of the earth. This quiet resistance to the obvious truth persisted even as the scientific revolution began to gather momentum in the 17th and 18th centuries. Enlightenment thinkers, armed with observation and mathematics, were rewriting the rules of the natural world. Yet somehow, meteorite falls remained stubbornly mysterious, relegated to the margins of respectable inquiry. Witnesses reported seeing stones fall during meteor showers. Credible farmers, priests, and officials swore to it. But without a coherent mechanism to explain how such a thing was possible, their testimony was often dismissed as folklore, perhaps exaggeration, possibly delusion, born of the night sky's power to confound the senses. The shift came, as so many shifts in science do, through the work of a single dedicated mind. Ernst Florenz Friedrich Chladni was a German physicist and naturalist who lived through the 1700s, a man of meticulous observation and unflinching logic. In the year 1794, Chladni did something remarkable and simple. He gathered together all the reports of meteorite falls that he could find, accounts from across Europe and beyond, written by observers of varying credibility and social station, and he organized them. He analyzed them. He looked for patterns. What he noticed, with the clarity of hindsight, seems almost obvious now. The falls occurred during the nights of known meteor showers. The falls were preceded by the characteristic sounds and lights that accompanied those shower events. The trajectories reported by witnesses, when mapped and studied, suggested objects entering the Earth's atmosphere from space. The composition of the recovered stones was unlike anything known to be quarried or formed naturally within the Earth itself. Through this patient assembly of evidence, Chladni constructed a thesis that was quiet but profound. Stones did indeed fall from the sky. They originated not in the clouds or the upper atmosphere, but in the vast gulf beyond the Earth itself. They were, in essence, fragments of the cosmos made solid, pieces of the ancient solar system that occasionally intersected the planet's path through space. He published his findings in 1794, in a work that gathered both scientific reasoning and the accumulated testimony of reliable observers. The idea was revolutionary, and yet it was presented with such methodical care, such an absence of sensationalism, that it began to shift the collective understanding. But acceptance came slowly. Chladni himself faced considerable skepticism from the scientific establishment of his time. How could matter exist in the vacuum of space? How could it survive the passage through the atmosphere? These were not frivolous objections. They were genuine puzzles that demanded solutions. Yet Chladni had done something equally important. He had made the question respectable. He had shown that the accumulated observations of meteorite falls could not be dismissed, that they pointed to a real phenomenon worthy of serious study. The final vindication came, as these things often do, through an event too dramatic to ignore. In 1803, a meteor shower occurred over the French town of L'Aigle, near Normandy. In the space of a few hours, thousands of stones fell across the countryside. The fall was witnessed by dozens of people, happened in daylight hours, and resulted in meteorite fragments that were immediately collected and studied. The French Academy of Sciences dispatched investigators. The evidence was overwhelming. The stones had genuinely fallen from the sky during the shower. Chladni's thesis was vindicated, and with it came a fundamental expansion of human understanding. What is perhaps most soothing to contemplate, in the stillness of such historical reflection, is how the shift from superstition to science was not a violent rupture, but a slow, methodical accumulation of evidence. Chladni did not dismiss the ancient mythologies or the folk traditions of meteor watching. He simply asked a different question. Not what does this mean, but what is actually happening. That shift in framing, from interpretation to observation, from celestial messages to physical reality, opened a door that would never close. The universe was no longer simply a stage for human spiritual drama. It was also a place of genuine material processes, of rocks and dust and orbits, of physical laws that applied equally to the heavens and the earth. The comforting realization is that this knowledge changed nothing about the experience of watching a meteor shower. The light is still beautiful. The sense of scale is still overwhelming. The feeling of standing beneath an ancient cosmic event is still profound. But now, beneath that wonder, there is also understanding. The stones are real. They have journeyed for millions of years through the void, and in their arrival, in their brief and brilliant descent, they carry with them the story of the solar system's formation, a narrative written not in mythology but in rock, in iron, in the composition of matter itself. Now imagine, for a moment, what happens when one of these ancient fragments encounters our world. A meteoroid, traveling through the silence of space at speeds that seem almost impossible to grasp, perhaps 40 kilometers per second, or 60, or even 70, meets the upper reaches of Earth's atmosphere, and here begins a transformation so gradual, yet so fundamental, that it has taken us centuries to fully understand what we are witnessing when we see that familiar streak across the night sky. The atmosphere itself, that thin, invisible ocean of air surrounding our planet, is not truly empty. Even at altitudes where astronauts once thought the void began, there are molecules, countless molecules of nitrogen and oxygen and trace gases, growing steadily denser as you descend toward the surface. And when a meteoroid, traveling at its incomprehensible speed, plunges into this realm, something remarkable unfolds that is both violent and, in its way, deeply gentle. The science here is one of friction, though perhaps not friction as you have felt it with your fingertips. This is friction on a scale that generates tremendous heat. But the details of how this happens have a soothing quality to them when you understand them fully. The meteoroid does not simply grind against the air molecules as a block of wood might grind against stone. Instead, the sheer speed compresses the air in front of it. Imagine pushing your hand through water suddenly, and the water piles up before you. Now imagine the air doing the same thing, but happening so rapidly that the compression itself generates extraordinary temperatures. This is called ram pressure, and it is one of nature's quieter miracles. The meteoroid, in a sense, is compressing a cushion of air so quickly that the energy of that compression converts into heat. The molecules in front of the meteoroid glow. They become ionized, their electrons knocked loose from their atoms, and in that ionization, light is born. Not the meteoroid itself, burning away through friction with the ground, but the air around it, luminescent with the energy of the meteoroid's passage. And here is where the physics becomes particularly soothing to contemplate. The meteoroid begins to ablate. This is a gentle word for a gradual erosion, and while the temperatures involved, sometimes reaching 2000 degrees Celsius or more, seem anything but gentle, the process itself unfolds with a kind of quiet inevitability. Layers of the meteoroid's surface vaporize, turning to gas and dust, adding to the luminous trail we see from below. Some of these ablated particles then create their own small friction with the surrounding air, their own tiny luminescence, contributing to the glow. Think of it this way: the meteoroid is not simply burning up in a single violent instant. Rather, it is being carefully, methodically worn away by the gentle pressure of an entire atmosphere moving past it at tremendous speed. The atoms and molecules of the meteoroid are being liberated from their crystalline structure, sent out into the air as dust and gas, eventually to be scattered into the wind currents of Earth's upper atmosphere. The trail we see, that glowing line across the night sky, is not the meteoroid itself, but rather the ionized air and the ablated material from the meteoroid's surface, excited by the sheer energy of the encounter. Different elements glow with different colors. Iron and magnesium produce the yellow and green hues so often seen in meteor trails. Silicates create the red edges of the brightest meteors. And the variation in brightness along the trail? That tells a story too. It speaks to the meteoroid's composition, to the variations in the air density it is passing through, to the slight tumbles and rotations of the object as it descends. Most meteoroids are small, the size of a grain of sand, or smaller. For something so tiny, the encounter with our atmosphere is catastrophic and complete. It vaporizes entirely in a moment that lasts only a second or two, sometimes less. And yet in that brief instant, enough light is released that someone looking up from Earth can see it clearly. A piece of dust becomes briefly more visible than the stars themselves. Larger meteoroids have a different story to tell. A meteoroid the size of a marble or a walnut may survive the descent through the thickest part of the atmosphere. The heat may be intense, yes, but the interior of such an object remains far cooler than the surface. A black crust forms, a fusion crust, created as the outer layers melt and then rapidly cool in the thin, frigid air of the upper atmosphere. By the time such a meteoroid reaches the lower atmosphere, where the air is much denser, its velocity has slowed considerably. The forces that once threatened to vaporize it entirely have eased, and if it is large enough and tough enough, it may survive the final descent intact, to strike the ground as a meteorite. The glowing trail that marks a meteor's passage, then, is really a story told in light. It is the visible record of energy exchange, of an object from another world spending its final moments in intimate contact with our atmosphere. And what could be more poetic than that? An ancient fragment, traveling in silence through the vacuum of space for perhaps millions of years, finally finding voice in the air surrounding our planet. The friction becomes light, the descent becomes beauty. What begins to emerge then, when scientists examine these ancient visitors more closely? when they hold a meteorite in their hands and study its grain and structure, is something far more intimate than a story of rocks falling from the sky. It is, quite literally, a message written in stone about the very infancy of our solar system, about the moment, some 4.5 billion years ago, when dust and ice and rock first began to gather and coalesce in the darkness. There are three primary categories of meteoroid composition, and each one holds a different whisper of the past. The stony meteorites, the most abundant kind, are composed largely of silicate minerals, olivine and pyroxene, compounds of silicon and oxygen and iron that form the basic building blocks of terrestrial rock. When you imagine a meteor streaking across the autumn sky, burning bright and brief, you are often witnessing one of these stony bodies entering our atmosphere. They are, in a sense, the most common travelers, and they arrive bearing the ordinary dust of the early solar nebula. But there is something quieter, more patient, in studying what they tell us. Embedded within these stones are sometimes tiny spheres called chondrules, small, rounded formations no larger than a poppy seed, yet each one a perfect record of heating and cooling that occurred in the solar nebula itself, long before planets had fully formed. These chondrules suggest that the young solar system was far more violent and chaotic than we once imagined, filled with countless collisions and heating events that melted and reformed material again and again. When you hold a stony meteorite and peer at these granules within it, you are holding direct evidence of that ancient tempestuousness, preserved and silent. Then there are the iron meteorites, the celestial siblings forged in a wholly different manner. These are remnants of planetary cores, fragments, scientists believe, of differentiated asteroids that once orbited the Sun and whose metallic hearts were exposed when collisions tore away their rocky mantles. Iron meteorites consist primarily of iron and nickel, often in extraordinary proportions, with trace elements that hint at the precise conditions of their formation. When a piece of iron meteorite is etched with acid and examined under magnification, a crystalline pattern emerges, called a Widmanstätten pattern, geometric designs of extraordinary regularity that reveal the slow cooling process that occurred within an ancient planetary body. This pattern cannot form quickly. It requires millions of years of gradual temperature decrease, a kind of patient metallurgical memoir written in metal. The presence of these iron meteorites carries a profound implication. It suggests that the early solar system contained not merely a cloud of dust, but a diversity of small worlds, each with its own internal structure and chemistry. Some differentiated, meaning their cores and mantles separated due to gravity and heat, while others remained more homogeneous. The meteorites that reach us now are the orphaned remnants of those ancient bodies, flung into space by the gravitational dance of the developing planetary system, eventually drawn into the inner solar system where their paths might cross with Earth. And there is one more category, rarer and yet perhaps most evocative of all, the carbonaceous chondrites, meteorites rich in carbon compounds and water. These are the most primitive in composition, less altered by heat and chemical change than their cousins, and they represent material that formed in the outer reaches of the solar nebula, where temperatures were far cooler. Some carbonaceous meteorites contain up to 20% water by weight, bound into minerals, a legacy of an ancient solar system in which water ice was abundant and distributed throughout the planetary building zone. When scientists analyze these meteorites, they sometimes detect organic compounds, amino acids, even the building blocks of DNA, suggesting that the ingredients for life itself were present in the solar system from its very earliest moments. What emerges from this careful study is almost humble in its revelation. The meteoroids that cross our sky are not exotic visitors from some distant realm. They are, rather, fragments of our own neighborhood's childhood. pieces of the same cloud of material from which Earth itself coalesced. They are siblings, scattered and aged, returning to us with information about where we came from. The iron within them might once have been part of the core of a dwarf planet. The water frozen within the carbonaceous varieties reminds us that our oceans and our biology have roots that stretch back to the solar system's formation. The stony varieties, with their chondrules and their silicate minerals, speak of collisions and reformations that occurred while planets were still being born. This is why meteorites matter so profoundly to scientists, and why they matter equally to those of us who simply gaze upward on a clear night. Each one that falls carries encoded within its structure the answer to a simple, eternal question. What were we made of at the beginning? And the answer, always, is this: the same materials that comprise these falling stones. We are stardust, yes, but more specifically, we are stardust that crystallized in the solar nebula, cooled slowly over millions of years, gathered together through gravity and chance, and eventually found ourselves arranged in the improbable pattern we call consciousness. The quiet truth is that when you watch a meteor fade from the sky, what you are witnessing is not destruction. You are witnessing a return, a long-delayed homecoming of the solar system's own ancient material, coming to rest in the atmosphere that sustains your life, arriving after billions of years with a message about origins written in iron and stone and ancient water, a message so profound that it requires no words. These fragments of comets, scattered across the solar system like the final pages of an unfinished story, find their way into Earth's atmosphere in patterns so reliable that astronomers have given them names and people have watched for them across centuries. The Perseid meteor shower arrives each August, when our planet drifts through the debris trail left behind by a comet called Swift-Tuttle, a comet that swings near the Sun every 133 years. As you lie beneath the August sky, the meteors you see are pieces of that ancient visitor, particles released millions of years ago, each one now moving at roughly 37 miles per second. The shower peaks around mid-August, though if you watch the nights before and after the peak, you'll still catch these slow, bright lines tracing the darkness. The Perseids are often the most generous of all the annual showers, sometimes offering dozens of meteors per hour at their height, and there's something almost ritualistic about how people gather each summer to witness this return, this punctual gift from a comet we last saw in 1992. Then comes the Leonid shower in November, a display associated with Comet Tempel-Tuttle, a visitor on an even longer cycle, returning every 33 years. The Leonids are gentler through most years, offering perhaps 10 meteors per hour, but there's something poignant about their relative scarcity, because it makes each one feel precious. Observers throughout the 1800s documented spectacular Leonid storms, nights when the meteors fell so thickly that people reported reading by their light, as if the sky itself had caught fire. These storms don't happen every year. They cluster around the years when the parent comet has recently passed near the Sun and its debris trail is still tightly packed. Scientists can predict with considerable precision when these outbursts might occur, yet there remains a tender uncertainty in all such forecasts, a reminder that the solar system, for all our calculations, still holds small mysteries. And then, arriving as autumn surrenders to winter, comes the Geminid shower in December, perhaps the most curious of all, because Geminid meteors don't come from a comet at all. Most meteors trace their origin to icy comets, but the Geminids appear to originate from an object called 3200 Phaethon, which has been classified as an asteroid, though it behaves somewhat like a comet, releasing dust and debris as it orbits. The Geminids are relatively young, geologically speaking. They were first clearly recorded only in the mid-1800s, suggesting that Phaethon's debris trail has only recently been crossing Earth's orbital path. It's a reminder that the solar system is not static, that new meteor showers can emerge, that the sky offers surprises even to those who have watched it for a lifetime. The Geminids peak in mid-December, often producing over 100 meteors per hour at their height, and there's something almost gentle about receiving such abundance in the depths of winter, when the nights are longest and the darkness feels most complete. What makes these showers so reliably return is a dance of geometry and gravity that unfolds silently across millions of miles. When a comet swings through the inner solar system, heated by the sun's warmth, it sheds material, ice, dust, and small rocky fragments, all along its orbit. Over time, these particles don't remain concentrated in a tight trail, but gradually spread out along the entire path the comet travels. Earth, orbiting the Sun on its own path, crosses these ancient trails at the same points in space each year, because orbital mechanics are deeply, almost beautifully predictable. The Perseid Trail exists in August space because comet Swift-Tuttle's orbit carries it to a point where it intersects Earth's path in August. The Leonids return in November because that's when Earth's orbit carries our planet through the debris left behind by Tempel-Tuttle. The Geminids arrive in December because that's where the Phaethon debris trail drifts. It's a kind of celestial rhythm, ancient and unchanging, yet newly lived through each time we experience it. The trails themselves are diffuse, dispersed across vast stretches of space, which is why a meteor shower doesn't feel like a bombardment. Instead, it's a gentle visitation, a trickle of particles arriving hour after hour, each one a small guest entering the atmosphere from the black. During the peak nights of the best showers, if you lie outside in a truly dark place, away from artificial light, you might see meteors arriving every few minutes, not constantly, but often enough that you fall into a watching rhythm, a patient alertness that has its own meditative quality. Your eyes scan the sky, knowing that a meteor could appear anywhere, that the next spark of light might emerge from any quadrant of the heavens. This uncertainty, this gentle attention without strain, is one of the gifts of meteor watching. Different parts of the world experience the same showers in different ways, depending on latitude and local conditions. From the equator, the meteors appear differently than they do from polar regions, because the angle at which Earth's atmosphere meets the incoming debris varies with geography. Observers in the northern hemisphere have traditionally had easier access to the Perseids and Geminids, while the southern hemisphere enjoys the Eta Aquariids in May and the Delta Aquariids in July, showers created by fragments from Halley's Comet and other solar system wanderers. These showers have created their own traditions, their own watching communities, their own quiet nights of gathering and gazing. In some regions, watching a particular meteor shower has become woven into the cultural calendar, a moment when families step outside together, when the cycles of the heavens are briefly acknowledged in the cycles of human life. The intensity of these displays varies from year to year, sometimes predictably, sometimes with small surprises, that keep astronomers and observers alert. A few years of strong activity, then years of quieter return, then perhaps an unexpected outburst when calculations suggested otherwise. This variability adds a soft suspense to meteor watching, a reason to return each year even if you watched the same shower before. The universe, in other words, has not made us bored. It offers enough predictability that we can organize our lives around these events, enough uncertainty that each night beneath the stars retains an element of discovery. The major showers, Perseid and Geminid and Leonid, have become the anchors of the astronomical year, moments when ordinary people and professional scientists alike turn their attention upward, when the debris trails of ancient comets make themselves known in brief, glowing lines against the dark. Now here is where the meteor shower transforms from simple spectacle into something far more intricate and beautiful, a dance of gravity and orbit so perfectly synchronized that we can predict it years in advance. like some ancient rhythm encoded into the very fabric of celestial mechanics. The meteors you see streaking across the August sky during the Perseids, or blazing through December during the Geminids, are not random. They follow a pattern as old as the solar system itself, and Earth passes through these same glowing corridors of dust at nearly the same time every year, with a regularity that almost feels like clockwork, except that the clock has been ticking for millions of years. To understand this, we must think of orbits as paths, and think of comet debris as breadcrumbs scattered along those paths in space. A comet, a massive ball of ice and rock traveling through the void, follows an elongated, elliptical orbit. Some of these orbits bring comets close to the Sun, where the solar heat vaporizes their icy surfaces, causing them to shed material. Dust particles, fragments of rock and ice, stream away from the comet's nucleus and begin their own journey through space, separated from their parent body but forever bound to the same orbital path. Over time, over centuries and millennia, successive passes of that same comet deposit more and more material into this invisible river of debris. The orbit of the comet becomes a stream of particles spread across millions of kilometers, a ghostly trail through the darkness. Earth, meanwhile, travels its own orbit around the Sun, and here is where the geometry becomes quietly miraculous. If Earth's orbital path intersects with that ancient stream of cometary dust, then Earth must pass through it. Every time Earth reaches that specific point in its yearly journey, it glides through the debris field, and the particles collide with our atmosphere at tremendous speeds, often 30, 40, even 70 kilometers per second, speeds so vast that the friction with air molecules ignites them in brilliant, fleeting streaks. For a week or two, the shower appears, night after night, as our planet drifts through the dust. The Perseid meteor shower, one of the most beloved, comes from debris left by the comet Swift-Tuttle. That comet orbits the Sun roughly every 133 years, and its debris trail has been accumulating for thousands of years. Earth intersects this trail in mid-August, year after year, without fail. The timing is so precise that ancient astronomers, though they did not understand the mechanism, could predict that meteors would appear in August. The Chinese recorded Perseids more than 2,000 years ago. Now we understand why. We have mapped the orbital mechanics and can calculate when Earth will pass through each stream. The actual density of particles in these streams is remarkably diffuse. The comet debris is not clustered tightly together. If you gathered every particle in a single Perseid meteor shower, every streaking light you see, their combined mass would be no more than a sand grain, perhaps smaller. Yet because Earth travels through that stream so quickly, at 30 kilometers per second relative to some of these particles, we see dozens or hundreds of meteors in a single night if we watch for several hours. The brevity of each meteor, most lasting only a few seconds, belies the immensity of the collision. A particle the size of a grain of sand, striking the upper atmosphere at such velocity, releases energy equivalent to a small explosion, and in that energy, we see light. The seasonal rhythm of the showers arises from the geometry of Earth's orbit and the location of each debris stream. The Leonids appear in November because that is when Earth's orbit carries us to the position where the comet Tempel-Tuttle's debris waits. The Geminids arrive in December from a different debris field entirely. The Quadrantids announce January. Each shower is a sort of cosmic appointment, a date that Earth keeps with an ancient comet's ghost, and our planet is so vast, so massive, that it cannot help but sweep through these particles and ignite them in the night sky. What makes this even more poignant is that these debris trails are not eternal. Solar radiation, the solar wind, and gravitational perturbations from Jupiter and other planets slowly disperse the particles, wearing them away from their original orbits. A meteor stream, when it is young and fresh, close to the time of the comet's passage, might be dense and brilliant, producing hundreds of meteors per hour. But over tens of thousands of years, the stream disperses, the particles drift, and the meteor shower weakens. The Leonids, which once produced storms so intense they darkened the sky with thousands of meteors per minute, have quieted considerably in recent centuries. And yet they persist. The shower continues. The ritual goes on. Earth's motion through the cosmos is thus a journey through time as well as space. Each time we enter a meteor stream, we are encountering dust that was ejected from a comet long ago, perhaps when human beings were just beginning to write, or paint, or build lasting structures. We are moving through the aftermath of events that occurred in the distant past, retracing paths that the solar system itself laid out millions of years before our species existed. The meteor shower, then, becomes a meditation on continuity, on the way that ancient events still cascade through the present, written in light across the night sky. And here is a subtle thing to consider. The orbits of these comets are slowly being perturbed by gravity. Jupiter's immense mass tugs on these ancient paths. Planets drift in their orbits over vast timescales, which means that the dates of meteor showers, while consistent over human timescales, are not fixed eternally. In a million years, Earth might pass through a meteor stream at a slightly different time of year, or miss it entirely, or pass through a denser portion and see more meteors. The order of the cosmos is not static but flowing, imperceptibly slow but eternal in its motion. The mathematics that describes all of this, the laws of orbital mechanics first formulated by Kepler and Newton, are themselves among the most beautiful that science has ever produced. They explain not only why meteors appear when they do, but the rhythm of all celestial motion. The same laws that predict the orbit of a meteor particle also govern the dance of galaxies, the motion of moons, the slow waltz of the solar system through the galaxy. In watching a meteor shower, you are witnessing the visible proof of gravity's patient ordering of the cosmos, a proof that arrives in streaks of light, season after season, predictable and eternal. Among all the meteorites that have ever fallen to Earth, certain arrivals remain fixed in the memory of science as moments of quiet awe. In 1947, in a remote corner of eastern Siberia, near the village of Sikhote-Alin, the sky opened in a way that very few people witnessed directly. A meteorite, traveling at roughly 40,000 miles per hour, entered the atmosphere on a February morning and fragmented into thousands of pieces as it descended. The event itself lasted only seconds, but what it left behind told a story that would take decades to fully understand. When researchers finally arrived at the impact site, months later, they found themselves walking across a landscape transformed. The forest was scorched in a radial pattern, trees flattened outward from the central zone like petals pressed from a flower. Nearly 190 tons of meteoritic material had fallen that day, scattered across 21 square miles, and as scientists began the patient work of collecting and cataloguing these fragments, something shifted in how they understood our relationship with the cosmos. What made the Sikhote-Alin fall so remarkable was not merely its size, though size certainly mattered. It was the opportunity it offered. Here was a meteorite fall recent enough that meteorites could be systematically recovered, studied in laboratories with precision instruments that previous generations could never have imagined, and analyzed in ways that revealed the true age of the solar system itself. The meteorites from Sikhote-Alin were iron meteorites, and their crystalline structure, when examined under magnification, showed patterns of cooling that had unfolded over millions of years. Scientists could hold in their hands, could slice open with diamond saws, and polish under electric light, fragments of a world that had died before the Earth itself was fully formed. The work was meticulous and unhurried, and in that patience there was a kind of meditation. Here is a fact that carries its own quiet poetry. Some of the iron meteorites from that 1947 fall are still being studied today, more than 75 years later, as new analytical techniques emerge and new questions arise about the composition of ancient stellar dust. But perhaps no meteorite in human history captures the imagination quite like the Hoba meteorite, which rests still, almost exactly where it fell, in northern Namibia, in southern Africa. Hoba is the largest known meteorite on Earth, weighing roughly 66 tons and measuring nearly 9 feet across at its widest point. And here is what makes it truly remarkable to contemplate. No one knows when it fell. There is no recorded event, no flash of light witnessed by human eyes, no crater of impact to suggest a dramatic arrival. It simply lay there, half buried in the red soil, waiting. When European settlers discovered it in the early 1900s, they found a meteorite so vast, so heavy, so utterly immobile, that they could do little but observe it where it rested. To study the Hoba meteorite is to encounter something that feels almost impossible, a visitor from space that refused to be moved, that demanded the scientists come to it rather than the reverse. The composition of Hoba is primarily iron and nickel, elements forged in the heart of dying stars and condensed into this singular, silent mass. When researchers finally examined it closely, they discovered that the surface showed signs of corrosion and weathering across the centuries, perhaps across millennia. The meteorite had oxidized slowly in the African sun, developing a patina that spoke of deep time passing overhead. And yet within that iron lay concentrations of metals and minerals, cobalt, phosphorus, tiny quantities of precious elements that told the story of the asteroid from which this mass had broken free, perhaps billions of years ago. Scientists who have studied the Hoba meteorite report a peculiar sensation, a kind of stillness that settles over you when you stand before it. There is no rush, no urgency. The meteorite has been waiting this long, it will wait longer still. Between these two falls, separated by geography and context and composition, lies a truth about meteorites that deserves to sink slowly into your awareness. They are, almost always, gifts of peace. The dramatic impact events that captured human imagination, the extinction-level strikes that ended the age of dinosaurs, the theoretical impacts that civilization has feared, these represent only a vanishingly small fraction of all meteoritic falls. The vast majority arrive quietly, harmlessly. They burn up in the atmosphere without reaching the ground. Those that do land typically arrive in remote places, in oceans, in deserts, in the empty spaces between human habitations. The Hoba meteorite, that enormous mass, fell in a landscape so sparsely populated that its arrival went unwitnessed and unrecorded for perhaps centuries. Sikhote-Alin fell in a remote corner of Siberia, where the risk to human life was minimal. There is something almost gentle about this pattern when you begin to notice it. Across the eons, across all of human history, meteorites have fallen to Earth millions upon millions of times, and yet catastrophic impacts remain extraordinarily rare events, separated by intervals so vast that they barely touch the span of a human civilization. The meteorites themselves become, in the hands of scientists, objects of profound meditation. A meteorite that fell in 1966 in the Allende region of Mexico proved to be what is called a carbonaceous chondrite, meaning it was composed largely of carbon-rich material and contained tiny spherules called chondrules, droplets of primordial dust that had been flash-heated and cooled in the solar nebula, in the womb of creation itself. When researchers examined the Allende meteorite, they discovered within it grains of material, pre-solar grains they are called, that had formed around distant stars before the solar system itself existed. Hold that thought for a moment. Within this meteorite that fell to Earth just 50 or so years ago were particles older than the sun, older than the planets, older than the very light that now shines across the night sky. Scientists studying these meteorites often speak of the experience in language that approaches the spiritual, not because they abandon their instruments and precision, but because the precision itself becomes a gateway to wonder. The calm deliberation required to analyze these materials, the slow accumulation of data, the patient construction of hypotheses, these practices open a kind of doorway. There was a meteorite that fell in Wales in the year 1660, called the Hunbader meteorite, and its arrival created quite a stir in the scientific circles of the time, because meteorite falls were still, in that era, regarded with considerable skepticism. It was falling meteorites that finally, irreversibly, changed the minds of the scientific establishment. Before the direct observation and collection of fresh meteorite falls, before the systematic study of debris fields like the one at Sicote Alin, the question of whether stones truly fell from the sky remained contentious. Scientists were skeptical, as scientists often are, as they should be, but each new well-documented fall added another piece to the puzzle. Each new meteorite collected and analyzed and measured and contemplated added weight to the hypothesis that our world sits not in isolation, but in constant, gentle conversation with the cosmos beyond. The famous scientists of the 19th century who held meteorites in their hands, who felt the weight of them, who examined their surfaces with magnifying glasses and saw the fine crystalline structures locked within the metal, these men reported a particular kind of serenity. They had moved past the need to debate whether meteorites fell. They were now asking deeper questions. Where did they come from, and what could they teach us? As you drift now through these stories of meteorite falls, through the patient work of scientists in laboratories and in the field, allow the rhythm of their discoveries to slow your own thoughts. There is no urgency in understanding a meteorite. The work unfolds at its own pace. A sample collected in 1947 is still yielding secrets 7 decades later. A meteorite that fell in northern Namibia, perhaps centuries ago, remains where it landed, patient and unchanging, waiting for the next curious mind to visit it and wonder at what forces compressed its iron into such perfect stillness, what cosmic journey brought it at last to this red soil beneath a foreign sky. And so we arrive at something that turns the entire history of our solar system into something you can hold in your hand. The meteorites that fall to Earth carry within them a message from the very beginning, fragments that have traveled for billions of years to reach us, and within those fragments lie whispers from a time before our sun was even born. Consider for a moment what it means to possess a stone older than the sun itself. In the 1960s and 70s, as scientists began analyzing meteorites with increasingly sophisticated instruments, they discovered something that should have seemed impossible. Embedded within certain meteorites were tiny grains, microscopic crystalline structures that predated the solar system by hundreds of millions of years, perhaps even a billion. These are called pre-solar grains, and they represent one of the most profound discoveries about the origins of everything around us. The light that falls across your eyes right now is powered by a sun that ignited roughly 4.6 billion years ago, when a vast cloud of gas and dust collapsed under its own gravity and ignited. But the dust from which that sun was born came from somewhere, and those pre-solar grains are survivors from the deaths of ancient stars, stars that exploded in supernovae long before our solar system existed. Some of these grains are silicon carbide, their crystalline structures so precise they could only have formed in the intense heat and pressure surrounding dying stars. Others are graphite, oxygen-rich compounds, even rare exotic minerals that exist nowhere else in the cosmos. What makes this so remarkable is that these grains somehow survived the violent birth of the solar system. They were incorporated into the primordial dust that swirled around the young sun, and they became locked into meteorites, rocky bodies that have protected them ever since. When you hold a meteorite, you are literally touching dust from the graveyard of ancient stars, material that witnessed civilizations rise and fall on worlds that no longer exist. The solar system itself, in its earliest moments, was a chaotic place. Imagine a vast disk of swirling particles surrounding the newborn sun, colliding, clumping together, slowly coalescing into larger and larger bodies. Within this disk, the pre-solar grains drifted. Some were destroyed by the heat and violence of planetary formation. Many more were incorporated into asteroids and comets. And the meteorites we find today are among the least altered remnants of that era. Time capsules sealed billions of years ago and only recently opened by human hands. Scientists studying these meteorites discovered that different regions of the disk had different compositions. The inner solar system, closer to the sun's warmth, contained more rocky material and metals. The outer regions retained more of their volatile compounds, ices and organic molecules. By analyzing meteorites, researchers could reconstruct a map of the young solar system, understanding not just what it was made of, but where different materials came from and how they were distributed. Some meteorites show evidence of having been heated and altered, suggesting they came from larger bodies where radioactive elements warmed the interior. Others appear almost pristine, preserved from the solar system's infancy. The pre-solar grains within meteorites carry isotopic signatures, subtle variations in the atomic weights of their elements, that reveal their origins in specific kinds of stars. Certain ratios of oxygen isotopes, for instance, point to origins in particular types of supernovae or in the atmospheres of dying red giant stars. Neon isotopes tell stories of cosmic ray bombardment in space, marking time between the grain's creation and its incorporation into the solar system. Each grain becomes a small detective story, and scientists spend years analyzing single grains to extract their secrets. What strikes many researchers who work with these materials is a kind of profound quiet. You examine a grain so small it's visible only under a microscope, and you realize you're looking at something that has survived for nearly 7 billion years. The violence of supernova explosions, the chaos of planetary formation, the impacts of asteroids, the passage of incomprehensible time, and still this grain remains, bearing witness. These meteorites have also taught us something unexpected about the abundance of certain elements. Carbon, which is essential for life, appears to be somewhat enriched in meteoritic material compared to what theory alone would predict. Organic compounds, the building blocks of living things, have been found in carbonaceous meteorites in astonishing variety and complexity. Some researchers have wondered whether meteorites and comets falling to early Earth might have delivered not just raw materials, but some of the chemical building blocks necessary for life itself. This isn't to say that life came from space. The evidence still points to Earth as life's cradle, but rather that the solar system may have prepared the ingredients long before our planet was ready to receive them. The abundance of water in meteorites also tells a story. Some carbonaceous meteorites contain water locked within their mineral structures, suggesting that a significant portion of Earth's oceans may have come from impacts by water-rich bodies in the early solar system. When you drink water, some of those molecules may have originated from asteroids formed in the outer solar system billions of years ago, transported here by ancient collisions. You are literally in contact with the solar system's deep past. And perhaps most profoundly, meteorites have shown us that the solar system was not born from a uniform cloud. Instead, it was a complex system with gradients of temperature and composition, with different regions containing different ratios of elements and compounds. By studying pre-solar grains and the other materials within meteorites, scientists have been able to construct models of how the solar system evolved, how planets migrated across the disk, how collisions shaped the distribution of matter, Each meteorite is a page in a vast cosmic history. The preservation of these grains and minerals across billions of years is itself remarkable. For them to have survived, the parent meteorite must have avoided reheating, chemical alteration, and the destructive forces of space weathering until it arrived at Earth. This is why meteorite scientists are so careful in their handling, why they preserve samples in controlled environments, sometimes even returning them to space to study how they change under vacuum and radiation. Every meteorite contains information that has traveled the long journey from the solar system's birth to this moment, and to damage or lose that information is to lose a voice from deep time. So the next time you consider a meteorite, whether in a museum display or an image in a book, or if fortune smiles upon you, holding one in your own hand, remember that you are touching a messenger from the ancient cosmos, a bearer of dust older than the sun, a keeper of secrets about how everything we know came to be born. And yet, for all the quiet beauty of a meteor's descent, we must pause here and consider something that shifts the story into a vastly larger frame. There is another tale, a darker, slower one, woven through the rocks that fall from space and the rocks that lie sleeping in Earth's crust. It is the story of extinction, and it is as old as our world itself. 66 million years ago, there was a morning. We do not know which morning it was, only that it came. And on that morning, something arrived from the void, a meteoroid perhaps 10 kilometers across, born in the asteroid belt between Mars and Jupiter, having drifted through space for billions of years. It struck the Yucatan Peninsula at a speed of 20 kilometers per second. The energy released was so immense, so overwhelming, that it reshaped the entire planet's fate in a moment. But let us slow down. Let us sit with this quietly. The impact site, called Chicxulub, created a crater 150 kilometers wide. The shock wave traveled outward in all directions. Forests ignited instantly. The ground liquefied. But what happened next? What happened in the days and months and years that followed? That is where the story truly lives. The collision threw billions of tons of rock, dust, and ash into the atmosphere. Sunlight itself became scarce. Temperatures plummeted. Plants, dependent on photosynthesis, began to fail. And when the plants failed, everything that fed on them began to starve. The dinosaurs, those magnificent creatures that had reigned for 160 million years, could not survive what came next. Neither could the vast majority of life on Earth. 75% of all species vanished in what we might think of as a geological instant, though it was really a span of thousands of years. An incomprehensibly long time in a human sense, yet mere moments in the calendar of the Earth. Now, here is something worth sitting with. This was not the only extinction event driven, at least in part, by visitors from space. There were others. The late Devonian extinction, 400 million years ago, may have involved meteorite impacts. The Ordovician mass extinction, 443 million years ago, possibly saw contributions from cosmic bombardment. We do not yet have certainty about these older events. The evidence is sparse, the geological record worn smooth by time, but the pattern is there, a rhythm of catastrophe punctuated by the falling of stones from above. And when we study these impacts, when we examine the layers of ash and iridium, that rare element from space, we begin to understand something humbling. The history of life on Earth is not merely the story of evolution and adaptation. It is also the story of interruption. It is the story of the cosmos asserting itself, violently and without warning, into the quiet affairs of one small planet. But here is another way to hold this thought, and perhaps a gentler one. Every extinction event, as catastrophic as it seemed to those creatures living through it, was also a clearing. It was a making of space. When the dinosaurs fell away, when the terrible lizards yielded the earth, the mammals, small, unremarkable creatures hiding in burrows, inherited a world they could never have conquered otherwise. We would not be here without that impact. You would not be sleeping beneath these stars were it not for a stone that fell from the sky 66 million years ago. The meteorites that fall today, the ones we watch with such peaceful wonder in summer nights, are cousins to that catastrophic visitor. They share the same origin in the same solar system that has been evolving for 4.5 billion years. Yet most of them arrive in silence, burnished by atmosphere, leaving nothing but a memory of light. There is a profound rhythm to this, if we can sense it without anxiety. The same processes that once reshaped life itself, the falling of stone and dust from the void, continue still. They continue in the Perseid meteors, in the Leonid display, in the slow rain of micrometeorites that falls upon the Earth every single day. We have been shaped by these arrivals. We are woven from the same cosmic dust that once transformed our world. And perhaps this is the deepest truth worth carrying into sleep. We are not separate from the cosmos. We are not safe from it, nor are we untouched by it. We are made of the same materials that fall from the night sky. The iron in your blood, the calcium in your bones, the oxygen in each breath, all of it was forged in distant stars or formed in the swirling nebula that birthed our solar system. Every time a meteor falls, it is a small reminder of that ancient kinship. The extinction events, terrible as they were, are part of that same story. They too are woven into the fabric of what we are. And knowing this, understanding that our existence is not separate from the falling of stars, but intimately bound to it, there is a strange and gentle peace in that knowledge. The very thing that once ended worlds also made space for ours. The sky that now rains down these quiet, harmless meteors is the same sky that held the power to reshape everything. And in that continuity, in that unbroken chain from the earliest days of Earth to this moment, there is a deep and ancient calm. The same meteor shower that paints the autumn sky over Tokyo will paint a different sky over Lima, over Cairo, over the forests of Scandinavia. The radiant point, that single spot in the heavens from which meteors appear to spring, stays fixed in the celestial sphere, yet the experience of watching shifts subtly with every latitude, every longitude, every hour of the night. In Japan, the Perseids arrive each August during Obon, the festival of ancestors, when families gather at graves and light lanterns to guide the spirits of the dead back to the living world. The meteors, falling through that same darkness where ancestral presences are thought to drift, become more than mere physics. They become part of a larger conversation between the living and the remembered. Grandparents point upward for children born since last year's shower, teaching them that the sky is alive with continuity, with cycles that outlast individual lives. The falling stars are woven into the fabric of remembrance. Cross the world toward the Mediterranean, and you find different eyes watching the same display. In Greece, where the ancient Perseid radiant falls not far from where Perseus himself, in mythology, drove through the sky, the cultural memory runs deep. The meteors become, once more, divine messages, though now framed less through superstition than through a kind of romantic archaeology. Modern Greeks watching the August shower sometimes recite fragments of Hesiod, calling the meteors shooting stars of antiquity, bridging the distance between their ancestors' awe and their own. The radiant point rises at different altitudes depending on your position on Earth. For observers near the equator, during the northern summer showers like the Perseids, the radiant climbs only moderately high, perhaps 30 or 40 degrees above the horizon, making the meteors travel at shallower angles across the sky, their luminous trails stretched thin and elegant. Whereas in northern latitudes, the same shower reaches nearly overhead, and the meteors plunge more steeply, faster, their brightness compressed into shorter arcs. The same shower becomes a different dance depending on where you stand. In the deserts of the Middle East and North Africa, where light pollution remains scattered and the Sahara opens like a vast darkened chapel, meteor showers carry particular weight. The Leonids, arriving in November, have historically been moments of profound cultural pause. In pre-Islamic Arabia, these meteors were sometimes read as signs of impending change. After Islam's arrival, the practice evolved. They became moments for prayer, for contemplation under an active sky, the universe demonstrating its dynamism. Even today, in regions where modern light has not yet drowned the night, families will sometimes gather on Leonid evenings, less from any formal tradition than from an inherited instinct that these moments merit attention. Indigenous peoples of the Americas have watched meteor showers for millennia, though their interpretations varied by tribe, by region, by the particular cosmologies embedded in each culture. Some Navajo traditions associate falling stars with the journey of souls. Some Pacific Northwest nations saw them as ancestors dancing. The vocabulary differed, the emotional weight differed, but everywhere the same curious impulse, to look up and find meaning in impermanence, to weave the sky's events into the story of how the world works. These traditions persist, attenuated by colonialism and displacement, yet still alive in some communities where elders teach young people to watch the sky not merely as spectators, but as participants in an ancient ritual of attention. The Southern Hemisphere experiences its own meteor showers at offset times, the April Lyrids visible from Australia, New Zealand, and Southern Africa. What strikes the listener is that the same cosmic debris streams that Earth passes through in the north create entirely different experiences in the south. The Perseids, so central to August traditions in the northern half of the world, appear from the Antipodes as a relatively modest display. Instead, the southern sky offers the Eta Aquarids in May, born from debris of Halley's Comet, and the Geminids in December, though the Geminids, interestingly, appear nearly equally splendid from both hemispheres. This asymmetry has meant that culturally, meteor watching became encoded in particular hemispheres at particular times. The Perseids, brilliant and reliably strong, became the meteor shower of the European summer, celebrated in literature and tradition. The inhabitants of Sydney or Cape Town developed different astronomical calendars, different expectations of when the sky would wake. When tourism and global communication accelerated, this created an odd phenomenon. Northern Hemisphere traditions of meteor watching became globally amplified through media and internet, while the rich southern traditions were sometimes overshadowed, their timing less synchronized with the narrative rhythms of the northern world. Yet there is something quietly beautiful happening now. Amateur astronomers and citizen scientists in every country, every continent, have begun coordinating observations of meteor showers in real time. Observers in Japan share their counts with observers in Brazil. Someone in South Africa reports a particularly bright fireball at precisely the moment someone in Portugal sees the same event. The ancient impulse to watch and interpret the sky has been extended across the planet, creating a nearly instantaneous web of attention. The meteor shower becomes, in a sense, a shared global event, yet experienced through the lens of local sky, local tradition, local season. In many Muslim-majority countries, meteor showers are sometimes noted during Ramadan prayers, their appearance considered auspicious by some observers, a sign of divine presence made visible. In India, where Hinduism reads the cosmos through the lens of endless cycles of creation and dissolution, meteors are sometimes framed as sparks from the cosmic dance of Shiva, the universe constantly remaking itself. In Christian Europe, the old superstitions have largely faded, yet the aesthetic remains. Church bells may still ring to announce a notable shower, and in some villages, watching becomes a communal act again, families gathering not in fear or for divination, but for the simple pleasure of shared wonder. There is a rhythm to how meteor showers move through human attention. In any given region, the arrival of the expected shower, whether the quadrantids in January or the Geminids in December, creates a small shift in the collective consciousness. News websites publish viewing guides. Observatories hold public nights. Families remember to look up. And in that moment, across hemispheres and borders and belief systems, something ancient reasserts itself. The human need to engage with the sky, not as background, but as presence, as something that touches us, that demands our attention and our awe. The meteor shower, then, is never truly the same event twice. Never truly the same shower, watched from the same place 2 years running. It arrives always into different cultural moments, different seasons, different arrangements of human life. Yet the core experience, that moment of lifting your gaze and seeing light fall from darkness, remains constant. A child in Manila and a child in Stockholm may not share a language or a calendar, but on certain August nights, they share the same falling stars, and that sharing, wordless and vast, connects them to something older than nationalism, older than writing, older than memory. The meteors fall the same way everywhere, yet differently, for everyone. In the quiet hours between midnight and dawn, across observatories and open fields, and the ceilings of amateur astronomers' garages, a vast invisible network hums with purpose. Modern science has woven itself into the sky in ways that would have seemed like magic to Ernst Chladni and his contemporaries. We no longer simply watch meteors fall and wonder. We measure them, we catalogue them, we listen to them with instruments that hear the whisper of friction against air. Radar, in particular, has transformed meteor science into something almost meditative in its precision. When a meteoroid slams into Earth's upper atmosphere at speeds of 10, 20, 40 kilometers per second, it doesn't just shine, it ionizes the air around it, creating a thin, luminous trail of superheated gas and plasma. That ionized column is essentially invisible to the human eye once the glow fades. But radar waves bounce off ionization like light off a mirror. Radio telescopes across the world, networks of them, calibrated and patient, transmit gentle pulses skyward every few seconds, and those pulses return altered, carrying signatures of meteors that fell minutes before, during the day when we couldn't see them, or so faint they never quite reached the threshold of human vision. The beauty of this is that the data accumulates with a kind of inevitable, patient completeness. A single radar station might detect hundreds or thousands of meteors in a single night, not in bursts of excitement, but in a steady, measured count that feeds into international databases. The International Meteor Organization receives reports from networks spanning continents, and the numbers grow, reliable, unhurried, like sand accumulating grain by grain in an hourglass. Cameras have joined this quiet vigil in recent decades. High-sensitivity video equipment, the kind that can detect the faintest glimmer, now points upward from locations around the globe, recording the sky in continuous loops. When a bright meteor streaks across the field of view, we call the brightest ones fireballs, those spectacular events bright enough to cast shadows on the ground. The camera captures it. And because these cameras are synchronized, because multiple stations observe the same event from different angles, scientists can triangulate position, angle of descent, speed. They can reconstruct the three-dimensional trajectory of a meteoroid before it became visible and after it faded, deducing where in space it came from and where its fragments, if any, might have landed. There's something profoundly soothing about this work, though it might not seem so at first. Picture a room lit by the glow of computer monitors, researchers moving slowly through the night shift, watching data streams, marking events, entering numbers into forms. The work is meticulous and unhurried. Nothing about it is urgent. These meteoroids arrived billions of kilometers away in their distant past. They will continue falling, whether we observe this one or miss it entirely. The science progresses one patient measurement at a time. And here the circle widens in a way that speaks to something deeper about how knowledge spreads. The work has also become democratic. Citizen scientists, people without formal training, have become essential partners in this vast monitoring effort. Smartphone apps now allow anyone with a clear view of the sky to report a fireball sighting, to record video, to submit observations through platforms designed to aggregate and validate these reports. Organizations like the American Meteor Society, the Global Fireball Observatory, and numerous international networks actively encourage this participation. A farmer in rural Kansas, or a student in Tokyo, or a retiree standing in their backyard can contribute real, usable data to the same datasets that professional astronomers use. Think about what this means. The night sky, which for so long was interpreted through the lens of profession and institution, has become a commons of observation once again, not in the mythological sense, but in something closer to it, a space where curiosity and technology align, where anyone awake beneath the stars can become a witness to something real and measurable. When reports come in of a particularly bright fireball, when eyewitness accounts converge on a location where fragments might have fallen, citizen scientists and amateur astronomers often mount expeditions to search. They comb fields and forests, they sift soil, they conduct their own careful measurements. Some of the most significant meteorite recoveries in recent decades have involved this collaborative web of professional and amateur observers working in concert. The meteoroid that fell near Sikhote-Alin in Siberia in 1947, spectacular as it was, occurred before these networks existed. Scientists had to piece together the story from eyewitness reports and fragments scattered across the landscape. But imagine if that same event happened today. Radar would have caught it. Security cameras and doorbell cameras across the region might have recorded it. Smartphone apps would have captured reports from hundreds of people. Satellites designed to detect bright fireballs would have registered the light signature. The data would be rich, immediate, collaborative. What emerges from all this technology and human attention is something that feels almost contradictory. The more precisely we measure meteors, the more we locate and catalogue them, the more they seem to speak to us of mystery and scale. A fireball's trajectory can be calculated to meters, its composition inferred from spectral analysis, its origin story deduced from its orbital elements, and yet each one remains a small, singular event, a piece of the solar system's history, tumbling through space for millions of years, burning itself out in seconds. Measured, studied, and still somehow unreachable, the data grows larger and more detailed, year after year, decade after decade, and so does our sense of the profound smallness of each individual meteor, and our own lucky place, standing here in the dark, watching, listening, wondering. And yet, when you consider the true arithmetic of what occurs on any given night, the scale of it becomes almost incomprehensibly tender. A meteor shower, you see, is not an event but a dispersal of ancient inheritance. The particles burning in our atmosphere, those luminous streaks that persist in memory long after the moment has faded, began their journey not years ago or decades ago, but sometimes hundreds of thousands of years in the past, traveling in the gravitational wake of their parent comets, as those comets slowly circled the sun, again and again. Each grain, each crystalline fragment no larger than a grain of sand or a pebble worn smooth by time, was once nestled in the frozen heart of a comet. And when that comet rounded the sun, the solar wind and gravitational perturbations gradually teased these particles loose, stretched them across the comet's orbital path into an invisible river of dust that persists long after the comet itself has vanished from the inner solar system. Earth's passage through these trails is, in a sense, a kind of reunion with something impossibly old. Consider the geometry of this alone. A meteoroid, drifting at roughly 40 kilometers per second, does not drift at all in any sense we might recognize. It races, it plummets, And yet, from the vantage of human scale and human timekeeping, it performs its entire visible life in less than a second. One moment there is nothing but starfield, and in the next, a brilliant thread of light blooms across the darkness, and then silence returns. The meteoroid itself has ceased to exist. Its kinetic energy, its brief momentum has been entirely consumed in the friction of our atmosphere. The heat generated by that collision, for that is what it truly is, a collision between a grain of matter traveling through the void and the entire weight of Earth's gaseous envelope, can momentarily raise the particle's temperature to thousands of degrees. The air around it does not merely warm, it ionizes. Electrons are stripped from atoms, light pours out, and then, as quickly as it manifested, the glow dissipates. What remains, in most cases, is nothing we could ever recover or observe. Most meteors are so small, so entirely consumed in their descent, that they evaporate into constituent atoms that drift down slowly with the ordinary dust and particles that are always settling through the atmosphere. A meteor is, in its fundamental nature, an act of almost invisible sacrifice, a transformation so complete that it leaves barely a trace. And perhaps this is why the experience of witnessing it feels so poignant, so weighted with meaning despite its brevity. We are watching something ancient become light, and then become nothing at all, in the span of a single blink. Yet the mathematics of it opens onto something darker and more wondrous still. On a single night during a major meteor shower, our planet passes through a debris trail so densely populated that hundreds, sometimes thousands of these particles enter the atmosphere simultaneously across the full span of the globe. Each one, in its own moment, performs this exact same transformation. On a night when the Perseids or the Geminids are active, the solar system is spending its vast inheritance, releasing ancient dust into light across the entire face of our world. There is no malice in it, no intentionality. It is simply what happens when orbit and composition and trajectory converge. And yet, from our perspective as conscious observers, there is something almost ceremonial about it, something that invites reflection. The dust that creates a meteor shower, remember, often originates from comets that have not visited the inner solar system for centuries. Some of it may have been part of their parent comet for millions of years. The Leonid meteor shower is produced by debris from comet Tempel-Tuttle, which orbits the Sun once every 33 years. Yet the dust that creates the Leonids was distributed across space long before any human civilization existed to witness it. We are, in a manner of speaking, passing through the archaeological layers of the solar system's history each time we stand beneath a shower and watch. The light that touches our eyes carried information. It carries atoms forged in the stellar furnace of the Sun itself, combined in forms that have not changed since the formation of the solar system. These are, quite literally, messengers from deep time. And what of the few meteoroids that survive their passage through the atmosphere? The larger ones, the more robust fragments whose composition happens to be stone or iron, rather than the more fragile carbonaceous varieties. These complete their descent and strike the surface as meteorites. They rest in deserts, in forests, in fields where humans might stumble upon them. These are gifts from the void, tangible reminders of a journey that required millions of years and countless gravitational influences to bring to completion. A meteorite sitting in a museum, or buried in soil waiting to be discovered, is a fulfilled contract. It arrived, it persisted, it can be held and studied and contemplated, whereas the meteor can only be remembered. There is something deeply humanizing about this recognition. Most of what falls from the sky does not wait for us. It does not complete its journey in any observable way. It arrives in fragments so fine that they simply become part of the air we breathe, the dust that settles on leaves and water and skin. We are, in a sense, constantly absorbing minute quantities of cosmic material, without ever recognizing it. The meteors we see, the bright ones, the memorable ones, are only the visible fraction of a constant rain that is entirely indifferent to our observation of it. The universe does not perform for us, though it can feel that way on a night when the sky is alive with falling light. And perhaps that is the greatest source of peace in contemplating meteors and their journeys. They remind us that immensity operates on its own schedule, that ancient things follow paths laid down by mathematics and gravity, not by intention or design. That transformation occurs whether or not we are awake to witness it. The universe will continue to shed its dust, will continue to birth light in our atmosphere, will continue to allow Earth to pass through these rivers of ancient debris, whether we watch or sleep. And in that indifference, strangely, there is permission. Permission to release our need to understand everything, to witness everything, to be present for every moment. Some things are beautiful precisely because they continue without our participation. Some light is meant to fall while we rest, and that is enough. And so we return, in this final moment, to that quiet field where we began. The night has grown deeper now, quieter still. The darkness around you is complete, pressing softly against the edges of your awareness like a gentle hand. Above, the sky continues its ancient work, indifferent, patient, eternal, and the meteors drift downward in their slow procession across the heavens. Imagine yourself lying there, your back against the cool earth, your eyes half closed and drifting. The grass beneath you holds the memory of the day's warmth, and the air moves across your skin with the faintest breath of wind. Your breathing has slowed to match the rhythm of the night itself. In and out, in and out. Each breath draws in the quiet and releases it again, until the boundary between your breath and the air becomes less clear. Above you, a meteor traces its final journey. You do not need to follow it with your eyes anymore. You know what it is now, a visitor from the ancient spaces between the stars, a fragment of a comet that fell toward the sun billions of years ago, drifting through the void for eons before finding this narrow window, this single night, this singular moment to announce itself to your watching eyes. And now it is gone. Its light fades into memory, dissolving into the same darkness from which it came. Think for a moment of all the meteors that have fallen through Earth's atmosphere in all the nights that have ever been. Trillions upon trillions, each one brief, each one bright, each one burning away in a moment so quick that it might have been merely a thought, a blink of the cosmic eye. And yet they all mattered. They all crossed this sky. They all wrote their small stories of fire and descent into the ledger of the night. Your thoughts begin to grow loose and wandering. Perhaps you find yourself wondering about the comet whose debris still drifts through space, still waits for Earth to pass through its trail next year and the year after that, a reunion repeated across centuries. Or perhaps you think of the scientists, centuries ago now, who first believed that stones could fall from the heavens, and how that belief changed everything we thought we knew about our place in the universe. Or perhaps your mind simply rests, without wondering at all, simply present to the gentle fact of stars and sky and the slow turning of the earth beneath you. The night deepens. Somewhere in the distance, an owl calls, a low, haunting sound that seems to come from the earth itself rather than the trees. The sound fades. More meteors fall, though you do not count them anymore. You simply feel them, the way you might feel rain on your face, a soft and distant presence that requires nothing from you but acknowledgement. Your eyelids grow heavier. The sky begins to blur slightly at the edges. The stars seem to shimmer and soften, as though they are moving farther away, or as though you are gently sinking deeper into the dark. It is peaceful, this dissolution. There is no struggle in it. Your body settles more fully into the ground, becoming, in a sense, part of it. Your boundaries grow less defined. And it occurs to you, in that drowsy, half-aware state that precedes sleep, that these meteors, these ancient, wandering fragments, are not so different from human lives, brief, luminous for a moment, burning away their energy in one bright arc across the darkness before returning to the void. And yet that brightness matters. That brief illumination changes the night. It is seen, it is remembered, it is held, in some small way, forever, in the memory of anyone who witnessed it. The thought is gentle and without urgency. You do not need to resolve it or understand it fully. You can simply let it settle, like dust falling slowly through still air, like a meteor descending through the atmosphere, slowing, cooling, fading into peace. Your breathing has become so quiet that you can barely hear it. The night breathes with you now. The meteors continue to fall, and you continue to drift, and there is no separation between watching and being watched. The sky holds you, the earth beneath you holds you, the ancient light of dying stars holds you in its gentle embrace. And as your consciousness grows thinner, as the boundary between waking and sleeping becomes less distinct, imagine that you are not simply lying beneath this meteor shower, but that you have become part of it, a small, stationary star yourself, waiting for the dawn, drifting slowly toward rest in the vast and patient dark. The meteors pass above you, before you, around you, and you pass with them, deeper and deeper into the silence, into the stillness, into the sweet and absolute peace of sleep that waits at the end of the night, as certain as the turning of seasons, as reliable as the Earth's slow orbit through the ancient and beautiful emptiness of space.